Yeah, it's very heavy. So anyway, we do have a pop quiz today. It starts at 10:55. The test number 3 is coming up. I have to get back to you with a date. I will open a window, very large window, like maybe 1 day or something, for you to take it at home. So it's open notes, and it's going to be a lot of conceptual questions with the right hands, because that way it's harder to use AI to find the answers. So you can always find the answers, but it will take you like an hour or 2 hours instead of taking you like 15 minutes if you pay attention in class. So if you pay attention in class, 15 minutes, you are done with the test. Okay, it's going to be on magnetism. Okay, I have to do this week and I have to get back to you. Okay, so again, right hands. We have many right hands, like 4. So 4 rules. First rule again, and the pop quiz is on conceptual questions. So the pop quiz today is like a review for test 3. So anyway, so if you have current flowing in this direction, or it could be positive charges flowing, okay, like protons flowing in this direction, okay. So the magnetic field is gonna curl around this way. Okay, so that's the first right hand rule. Second right hand rule, so I'm just reviewing. If you have loops of current, right? So a coil, it's called an inductor. So in that case, you use your right hand different way. So those fingers here will be the loops of current. Okay, so the current is going this way. Now the thumb here will show you the north. So it will behave like a bar magnet. That will be the north and that will be the south. Okay, so you can define in this case refresh. You can define in this case what we call the magnetic dipole. Okay, so I'm going to get back to that, but that will be the second right hand rule. Refresh. No, refresh like this. Yeah, it should. I don't know. It's canvas. I don't know what's going on. Third, good morning. Right hand rule. Here, it's the magnetic force, right? So, yeah, it's normal. You refresh. You can refresh. I don't know why. Okay, so third right hand rule. If the current is going this way, the magnetic field is going that way. So these are vectors. Then the force is coming out of your point. Okay, and that will be true for a positive charge moving at a given velocity or just current flowing. If you have a negative charge instead, you use your left hand. So negative charge or beam of electrons moving this way, magnetic field is up, so the force comes out of the palm. If you don't like this one, you can use this one. Okay, so if the current is this way or the positive charge is moving that way, magnetic field is this way, that will be the force. So you see the force is perpendicular. The force is perpendicular to the current, or the force is perpendicular to the velocity of the charge, which means the force cannot change the speed of the charge. It can only change its direction because it's perpendicular. Okay, you need a component of the force along the moving charge to make it go faster or slower. Okay, so this force is a deflecting force. A magnetic force is a deflecting force. It will deflect, but it cannot accelerate or decelerate. An electric force, so if you have a charge in an electric field, so yes, the electric field will accelerate or decelerate. A magnetic field can only deflect. And you have a magnetic force only, first of all, if you have a charge. Okay. Second of all, if and then if you have a component of the field, magnetic field perpendicular to the current. Okay, so if the current, typical pop quiz question or conceptual question, if the current is parallel or anti-parallel to the magnetic field, no force. Okay, so this is called a cross product, okay, from vector analysis. Okay, so we did that, and then we define each time you have a magnet, an electromagnet, a loop of current, okay, or it could be a proton spinning. Like you can imagine that a proton has a spin, so it's like current flowing. Then you can define a magnetic moment, which is a vector. It's a vector. So you take your right hand. This is your loop of current. Up here, that will be the vector magnetic dipole. By definition, the magnetic dipole in magnitude will be the number of loops times the current times the area. The area doesn't have to be pi r square. It could be width times length. Okay, and that will be the number of loops. It's a vector. Okay, that vector here is in the same direction as the normal vector. Okay, normal vector is perpendicular to the surface. Okay, so we did that last time. Just reviewing quickly. If you have a magnetic dipole, so it's going to be important for, again, test 3 will be focusing on conceptual questions and to see if you are able to use your right hand or not. Right, so it's all those rules. So anyway, if you have a loop of current here, the magnetic dipole wants to align with the magnetic field. If it's not aligned, there will be a torque. Okay, there will be a twisting force. So it will twist, it will rotate until you get this alignment between the magnetic dipole and the magnetic field. Agree? Now, if you wanted to flip against the magnetic field, you have to produce work. You have to twist in the opposite direction. That work will go into potential energy. Okay, so that's how we define potential energy, how much work you have to do to go against the magnetic field. So that will be conceptual question, lowest potential energy, highest potential energy. Okay, so that's how MRI works, right? So first the protons, I don't know why, just refresh, like, I don't know, I don't know why. It's canvas having issues. So like a MRI, you have those nuclei of hydrogen aligning the magnetic field. You excite them with the right frequency. So this is called resonance. They're gonna flip. Okay, they get high. Okay, and then when they relax, they're gonna burn out radio waves. So you're gonna be highlighted by radio waves, and you get tomography. Tomography image, an image of the inside. Okay, remember, a magnetic field always curls around out of the north into the south, never diverge, never converge. I know, I don't know why. I don't know why. I wish I knew, but I don't know. Okay, so you can draw the parallel with the electric field. So with the electric field, when you have a plus and a minus, okay, it's called an electric dipole, like the water molecule. So you can define an electric dipole. It's a vector, it goes from the minus to the plus. And what's going to happen if you have it in an electric field, again, it will rotate to get to the lowest potential energy to align itself with the electric field. So that was from the previous unit, and you can define the torque. Okay, that will be applied to an electric dipole to lower the potential energy. So that's how you can map an electric field with little seeds, right? They get polarized and they rotate and they align themselves with the electric field, and you can define an electric potential energy. Okay, so now we're going to do the same thing here. So we can define a magnetic dipole. Okay, so again, if I ask you here, you take square. See, this is your magnetic dipole. So it will rotate to align itself with the magnetic field. So if it's rotating this way, that will be counterclockwise. Okay? Now, fourth rule for the right hand, if something wants to rotate this way, okay, so if there is a force and it's trying to apply a twist, that means that will be your torque, the vector torque, okay? The torque is a vector. So that's a fourth rule. So in that case, you see it wants to go this way. So the torque is coming towards you. So the torque is out of the screen. Hey, stupid. Why don't we have a big screen here instead of having two screens? So this is a magnetic dipole. It wants to rotate this way because, and then you forget about that right hand. And then here it wants to rotate this way, so the torque is going towards you. Okay, so it's a vector. Okay, and from physics 1, don't forget, a torque is how efficient force is in applying rotation, making rotation happen. And it's a cross product. When you are finding the torque, you multiply the force times the distance here, but you are only using the perpendicular component because it's a cross product. Okay, so that's from physics 1. Okay, that's a very good YouTube channel, by the way, Physics Ninja. So the torque is a vector. It's a cross product between the distance between the axis of rotation where you're applying the force, cross the force. So you need to take only the perpendicular component of the force. Okay, so you can, I'm not going to teach physics 1 again. That's the idea. Okay, and then we're going to define the potential energy. So let's go back to the slide. So this is my kick side. Kick slides. I don't know where we start. Oh, by the way, someone, so there is a typo somewhere. No, I'm not in the right unit. This is the unit here. Okay, so here there was a typo. So we did that problem. There was a typo. It's missing a 0. It should be 0.086. So if you want to fix that from last time. So there was a typo here. Okay. Well, we did all that. MRI, we did that. Okay, did we do this one? Yeah, we did. We did, right? We did. So remember, fourth rule, if something wants to rotate this way, trying to rotate that way, that will be your vector torque. That's the fourth rule. Okay, so this here comes from Hyperphysics. It's a website. They have all, I mean, it's very useful for engineering. They have all the equations that you need. It's very well done, nicely done. So again, you're going to see the definition of the magnetic dipole moment. Again, it's a vector. If you have more than one loop, you're going to multiply by the number of loops. It's going to be the current times the area. And that will be the torque, definition of torque, right? So it's a cross product between the magnetic moment and B. So the magnitude, it's with a sign. So if you're just looking at the sign, the torque will be the number of loops times the area times B, in which the loop is placed, times the area of the loop, and that will be the sign of the angle between the magnetic moment and the magnetic field. Again, it's a cross product. So once they are aligned, the angle is 0. Sine of 0 is 0. There will be no torque because it's happy. Potential energy is the minimum possible, so no more torque. Okay, if it's 1 if it's 90 degrees, okay, you're gonna have the maximum torque. Okay, did we do this one? No? Okay, do this one. So I forgot my tablet, which happens once a semester. So I will have to use this, okay? So make sure you take notes because this is not recorded. Okay, I have to do hands low tech. I'm going low tech, okay? Hey. So they give you the area. Okay, so that's easy. Area is 2 times 10 to the negative 4 meters squared. And number of loops is 100. Okay, so do it. Don't wait for me. The current is 0.045 amps. So the magnetic moment in magnitude, it will be the number of loop times the current times the area. Okay, so just a numerical application. Do it. So 100, 0.045, and then 2 times 10 to the negative 4. Okay, did you do it? Just plugging in. I don't know if you can see. Can you all see? Otherwise, like it's empty, so you can move forward. So now I get that. Did you get that? Yes. Okay. Amps. So the unit is amps meter square. Okay, that's amps. Okay. B, find the torque. So in magnitude, okay, so the torque is the number of loop, or you could say it's the magnetic dipole times the magnetic field. And the angle, right? The angle between the magnetic moment and the magnetic field. Okay, so it's gonna be times 10 to negative 4. It's you have to refresh. If it's blinking, you refresh. Times 0.15 Tesla. Did you get that? Okay, 1.35 times 10 to negative 4. Did you get that? Yes. Okay. So you see unit, because the torque, the definition of torque from physics 1 is this, right? So that's in meters. This is in Newton. So this is in meters, Newton. Okay. And I should add here sine of 90.
Let's find an angle between the cosines and the hypotenuse.
Yeah. Do they? Oh, because they said the maximum torque. So if it's a good question. If it's a maximum torque, that means the angle is 90 degrees. Okay, the question. This comes from algebra base, so book, but it's a nice one. You remember that you have to open your textbook and do the solve problem as we go along, especially if you want to go to engineering or physics. Okay. Of course, I have to switch back and forth now. Okay, so lots of applications. So that was back then. before digital age, before the revolution of the semiconductors, we use this to measure. And in the lab, or you use them, or they are still using them, or you use them just as an experiment to show the deflection. Oh, okay. Galvanometer. Okay, but they use it to just to show you the magnetic force, right? Okay, that's cool. So that was back then, and everything was built in the US, right? So back in the 50s or before that, they built everything in the US, and they built these are beauties, right? It's like antiques. Um, you can still find them in labs because now we use multimeter, right? So it's all digital. But that was not digital. And the idea is very simple. You have a current flowing. So let's say you want to measure the current. So the current is flowing. Okay. So you have a loop of current. So you're going to have a magnetic dipole. So it wants to rotate. It's trying. Maybe it won't succeed because you have some resistance here. There is a spring. It's a coil, right? But it tries to rotate, okay, to align itself with the magnetic field from north to south. And then the amount is going to twist, depends on the force, and the force depends on the current. So it's proportional. And so then you can measure the current, and I am power anymore. So then you have to calibrate. Okay, so it's a very nice here. It's very well nicely explained, and you have the coil here. And instead, you can also measure the voltage because voltage equals current times the resistance. So you can do that too. So we talk about that, right? I brought you like a demo. So this one is a motor with a commutator. Now I show you the motor that you can build for extra credit. Okay, you have easy ones to build, but if you are in hands-on, you can do more challenging one. But the idea is, again, typical conceptual question. You take your right hand here, you see it's flowing this way, right? The magnetic field goes from north to south, so it's going to rotate that way. Okay, it's going to rotate this way. It wants to rotate that way such as the magnetic dipole will be aligned with the magnetic field. And then there is a secret. The secret is all of a sudden here it's losing contact. So because it's losing contact and it has some inertia, rotational inertia, it will keep spinning, okay? And then it will make contact again. So the motor I showed you last time, you sand, yeah, like you use a sandpaper, you remove all the varnish except 1/3. So at some point you lose contact and it keeps spinning. Okay, because if you don't have that trick, it will get stuck. It's happy. Okay, it doesn't want to keep spinning. Okay, it will be stuck there, and it will start oscillating. Okay, so we did that. Okay, a little bit more calculus here. Again, these are vectors. So you can write it this way. So that will be the vector area or the normal vector. Normal vector will be A, the area times N. That will be the torque applied, and that will be the potential energy of a magnetic dipole inside the magnetic field. Okay, and you have the lowest potential energy possible and the highest potential. So that will be the lowest potential is when the magnetic dipole is aligned. This will be the highest potential energy when it's anti-parallel, right? That's the idea of the MRI. You excite them and then they relax and they burp out radio waves. So these are the definitions. So that's for a dipole. Magnetic dipole, electric dipole, there is a symmetry here. Okay, you with me? So the lowest potential energy, that's what it wants. Okay, so let's try to do that. And again, I forgot my tablet. It comes from one of the free textbook that you find the link in Canvas. Okay, so try to do it because it's magnitude toward the right. Find the magnitude of the magnetic moment and the torque. View from above. So counterclockwise. Okay, so try to do it. So first you always start with the drawing. So I'm going to do it this way. You have a magnetic field here. I don't know if it's big enough. You are young, you have good eyesight. And this is my loop here. I'm going to make my loop like this way. Okay, so it's inside, like that. And here you have your magnetic dipole. Okay, so what's going to happen? So it's going to rotate which way? Very good, clockwise, very good. Clockwise because it wants to align itself with the magnetic field. So it will be acted upon by a torque. Okay. So clockwise, right hand, the fourth one, clockwise, means the torque is in the page. Right? Clockwise, let's start scrolling things. Okay, number 8. So do it. Find the magnetic dipole. So magnetic dipole equals the number of loops times the area times the current, right? So number of loop is 30 times the current is 5. The radius, we are the radius, yes, so it's pi r square. Okay, 1.2 amps meter square. Did you get that? Yeah. Now, if we want to take it professional, you have another right hand coordinate system. So if this is x, this is y, this is z, x, y, z. So if you take x this way, y, so x, y, z is towards you. This is z. So the magnetic dipole has a magnitude, it has a unit, and it has a direction which is y hat. Okay, so if you want to do it professionally, like with a x, y, z, you can use the y hat. Any questions? Are you with me? If you don't see, you can come closer. B, torque. Find the torque. Okay, the angle is 90 degrees. Okay, so the angle between mu and V is 90 degrees. Okay, that's good. So in magnitude, the torque will be your dipole times V times the sine. Okay, so do it. If you cannot see, come closer. So it's going to be 1.2. The magnetic field is 1.22. 1.2. Okay. It's about 1.14 Newton meters. Yes?
So that's 1.44. Yeah.
1.44. Thank you. 1.44. Okay, so that will be the magnitude. Now, it's a vector, and remember, we are using the right hand, the fourth one. So again, if it's rotating clockwise, the torque is going into the screen, which means it will be negative. It's along the negative z-axis. So the torque is 1.44 Newton meters, and it's minus z hat because it's a vector. Okay. Okay. Any question? Okay, so use the definition of potential energy to find the change in potential energy. The change in potential energy going from this position to the position, because what's going to happen to it? It's gonna do this, right? So this is minimum potential energy. That will be in the middle. Now, if it's the opposite, that will be the highest. So highest potential energy. Potential energy equals 0. Potential energy is minimum. So negative potential energy, the opposite, right? This is lowest. This is 0. And that will be maximum. So this is negative, 0, positive. Okay? Okay, so find the change in potential energy. So that potential energy here will be positive. That potential energy here is 0. That potential energy here is negative. So negative meaning it's bound. Potential energy is negative when it's bound. That means if you want to change the configuration, you have to work hard on it. Okay? Potential energy is negative when it's bound, right? So you have to do work to change it. That will be positive potential energy, so it's high, and that's in the middle, that will be 0. Right. So wait, so the potential energy, let's write the equation. It's minus mu dot B. Can you see? No, you don't see. Okay, potential energy by definition is minus the magnetic dipole dot the magnetic field. So there is a cosine here. Okay? So potential energy will be minus magnetic dipole times B times the cosine between U and B. Yes? By definition. I cannot go back to my slide because then I have to swing back and forth. Let's try to do it. So first we are here. Do you? Yeah. First we start with here. So what's the angle here between the magnetic field and the dipole? 90, right? Cosine 90 is what? 0. Okay, so the first potential energy equals minus, what's the dipole? 1.2 times 1.2 times cosine 90 degrees is going to be 0. But it's not the minimum. Minimum will be this one. So it's still not happy with life. Right? By definition, this is the definition of the potential energy. So after, once it spins, it's going to be what? What's the angle now? So fully aligned. So what's the angle? Huh? 180? No. 180 is this. This is what? What's the angle between those two vectors? What is the angle here? This is 90, 0, right? 0, 90, 180, 270, 360. So it's 0. Its cosine 0 is okay. Times cosine 0. So it's gonna be minus 1.4. Is that right?
Yes.
Joules. So the change in potential energy is after minus before, so it's negative. So what does it mean? It lost potential energy. Now it's negative. Now if you want to change that configuration, you have to sweat. That's the idea. Yes, I guess, right? You're right. So it could be, you're absolutely right. So absolutely. So if it's a motor, it will be kinetic energy, rotational kinetic energy. If it's a MRI, the energy will be radio waves. Okay, so it will be excited, right? So it will increase its potential energy by absorbing radio waves, and then when it comes back, it's coming back, it's going to burp out radio waves. So you are right, it's a conservation of energy. So if it's a motor, yes, you go from potential energy to kinetic energy. Okay, so I don't know if I have a nicer slide. Yeah.
So would it be easier for it to go from the zero position to like lowest potential energy than from lowest to highest potential energy?
So if you want to lowest to highest,
That would require the most work.
yes. And that's exactly, actually, it's a good question because that's exactly how potential energy is computed. To compute that potential energy, you're going to find the work done going from lowest to highest. And how do you find the work done? From physics 1, you're going to multiply the torque applied by the angle. Right? That's how you will do the computation. It's done in your book. Right? So going from the lowest to the highest, you have to do work. By finding this work, you find that definition. See if I can find another slide. Okay, so that will be the lowest, that's the highest, but I wanted to see the step in between. Anyway, so if I go back to here, so if you have a magnetic field going this way, okay, so that will be the lowest. Potential energy is negative. If it's against it, potential will be positive. Okay, it's like potential energy above the ground. Okay, so has potential energy which is positive, so maximum, minimum, and in between, potential equals zero. But it doesn't mean that this is the minimum. No, no, no. This is the minimum. Okay? Okay, okay. Video dipole. Okay, let's see if I have a video about a dipole. Okay.
In other words, the field exerts a torque that tends to make the North Pole point in the direction of the field. In fact, that's how the direction of the field is defined.
Okay, so they want to align. They want to be aligned. Okay, so lots application will be motors, electric motors. So it's a way to convert energy from electrical energy to mechanical energy. So the magnetic field is just a way to convert to transfer that energy. So here you have examples. Okay, and then we move to the magnetic force, but it's exactly like we already. It's not that far. Like so, here let's look at these equations here. So far we did that magnetic force, and if you massage a little bit this equation, you're gonna get to this one. Okay, because a current is a flow of positive charges. Blame Franklin Roosevelt. So here we have something very similar. So if you have a positive charge moving in this direction and you have a magnetic field going towards you, the force will be down. And again, that force is a deflecting force. So you have this equation, that equation. You just massage this one to get this one. You can look at your book. That is the magnetic dipole. That will be your potential energy there. Okay, so it's easy to understand here. Magnetic force. So sometimes it's called the Lorenz force. Lorenz force. So again, velocity of the positive charge going this way, magnetic field this way, that will be the force. So again, it's a cross product. If you have a negative charge, you use your left hand. Cross product. Okay? Still magnetic force. Okay, so the general equation is this way. This one. We've got Lorenz force, and I'm going to run out of paper. It's a magnetic force, but the general form is on a charged particle, okay, Q. If it's placed inside an electric field, the force is parallel to the electric field. So that force here, that electric force, will make the charge going faster or slower. But you can also include a magnetic force, right? So it will become QV cross B. And this is called the Lorentz force because you can have both. You can have an electric field and a magnetic field at the same time. Now, the thing to understand is that the electric field is like gravity, so it will accelerate. The magnetic force cannot accelerate. It will only deflect. It's a side force. Okay? So if for example you have a positive charge here going this way, and there is a magnetic field perpendicular to V, okay? So then the force will be perpendicular. Okay, let's see. Where is the magnetic field, do you think? Take your right hand. So this is the velocity, this is the magnetic field, the force coming out. So velocity this way, the force is going this way. So where is the magnetic field? Into the paper. Right? Into the paper. Do you all agree? Do you see? So into the paper. Yeah? Okay, so my right hand, velocity is this way, the force is going that way, and my arm hurts, the magnetic field is going into here. Are you sure? Because this is conceptual questions, you have to understand that. So it's a sideways force. So it's like physics 1, when you want to make a turn on the highway, it's from friction, the static friction. So the car wants to go in a straight line at a constant speed. No, you can't. Okay, it's going to be deflected. So it wants to go around. So a magnetic force can only deflect. It's called a cyclotron motion, and that's how a mass spectrometer will work. But the magnetic force is always perpendicular to the velocity only if the magnetic field has a component perpendicular to the velocity. So a magnetic force deflects. An electric force will accelerate. So if you have your positive charge, it wants to go this way, okay, minding its own business, right? And you have an electric field this way. So the force will be this way, but it will accelerate down. So it's not a circle now, right? It's gonna be a parabola. So it's like a projectile motion. So an electric force accelerate, decelerate, a magnetic force deflect. Okay? If you have an electric field, you can have the acceleration is the electric force over the mass, right? We did that. We found like you can go from potential energy to kinetic energy. There is an acceleration, force divided by mass. But here, it's a centripetal force because it keeps the charge on a circular path. Do you remember the centripetal acceleration? It will be mv squared over r. Okay? That will be the centripetal acceleration. And that force here will be the centripetal force. No, sorry. V squared over r, and the force will be mv squared over r. Okay, we're going to see that soon. But the idea is that the electric force, the magnetic force only deflect, and electric force accelerate or decelerate. Yes? Are you with me? You have to pay attention because it's the next test is heavily conceptual. And you have so many applications in technology. So anyway, you can do this experiment. It's a cathode tube, so CRT. So it used to be used in old TV or oscilloscope. So you have a cathode and you have an anode. You have electrons here. The filament gets very hot. The electrons break free. and they want to accelerate because here you have an electric field between the plus and the minus. The electron wants to go against the electric field, and you have some phosphorus so you can visualize the electron, and then you bring a magnet and the beam of electron will be deflected, not accelerated. Deflected. It's an acceleration, but it's a circular acceleration. Okay, deflection. You can do that to these old TV. These are analog TV. So when we were kids, we used to mess up with the screen. You will bring a magnet and you have those beautiful colors. That will be very abusive behavior.
One of the first art exhibits that were made for video art, just as its art form, I believe was Jim Pike, and the entire art exhibit was just that he bought a crap ton of TVs and then he gave everybody a ton of magnets and said, "Okay, have fun."
Ah, okay. That's interesting. You should see the things that they have in Paris in the art museum, modern art museum. It's totally nonsense. There is a artist. His name is Ben. Have you heard of him? Like, it's you really have to like modern art. I don't know if he's still on. J'ai trop d'idées. Okay, good for you. You know that kind of stuff. L'art est partout. Je ne comprends pas. And I don't know how much is going to sell this piece of art. Oh, typical here, like a mess. And then this is modern art. Okay. It's a tangent. Let's go back. So if you go in the old lab, maybe you see those oscilloscopes. So now oscilloscope to measure voltage, as a function of time, they use digital. This was analog. And that's used like a vacuum tube, CRT. So you have a beam of electron being deflected scanning the screen depending on the voltage applied. It's super cool. It was super cool because you could open it. And, okay. No, the cathode ray. No, this one.
And on we call screen, we notice that the electrons are emitted from the camera. Show the deflection of that stream. Here we can see the electrons being deflected. Then the cathode ray double.
You see, it's 90 degrees, right? The velocity is in your screen. The magnetic field is in or out. So the velocity is this way. The magnetic field is in or out, and the force is perpendicular to both the velocity and the magnetic field. So they are at right angle from each other, right? Okay, so the electron, and then you have to use your left hand because it's electrons. So that will be the velocity. And then let's say the magnetic field goes into the screen, so the force is down. If the velocity is to the right, magnetic field is towards you, the force is up. You have to use your left hand. Cool, right? Super cool. Okay. Okay, so you have the electric force that accelerate, decelerate. The magnetic force will deflect. So sometimes we have to know the right hand coordinate system. Let's see. Bing, bing. Okay, so I'm going to put only no magnetic field. So I'm going to remove the magnetic field here. And okay, and no velocity. Okay, no velocity whatsoever. So imagine it's at rest. What's going to happen to it? The electric field is up. So no. It's an electric field. There is no magnetic field. An electric field will accelerate, and you don't have an initial velocity to begin with, right? Exactly. It's gonna accelerate. An electric field accelerate. You know, you can have like a projectile motion. Okay, so it wants to go this way, but the force is that way. Okay, so you're gonna have a projectile motion upside down, like we did in electrostatic. You see, like a projectile motion, it's a parabola, but you see the velocity is increasing with time. Do you see that vector? So it's still accelerating. The x component of the acceleration is 0. Only the y component of the acceleration is not 0. The acceleration will be QE over m, but it's accelerating. Okay, it's a parabola. Now, if you have only a magnetic field, so if I remove this one, if I have no velocity, will I get a magnetic force? Nothing happens. Okay, for magnetic force to be, the charge has to be moving. No motion, no magnetic force, which is different than the electric force. Electric force, even if it's not moving to begin with, it's going to start moving. Here, it has to be moving. QVB, no V, nothing happens. So I need to have some initial velocity, and I have to start over. Okay. Okay, you can do it. Okay, that's nice. Okay. And you see what you get with a magnetic force, a magnetic field, it's going to go around a circle. Right? It depends now. If you have an initial y velocity, yeah, so the force, the magnetic force is always perpendicular to the velocity. So it's being deflected. So here it's totally perpendicular. Now, if I add another component of the velocity, but it's annoying because I have to start over. Okay, so I have a component here. So now you get something interesting. So you get what is called a still a circle, x and y. Okay, because the force, the velocity is still perpendicular. Oh yeah, because the magnetic field is in the screen, so the velocity is still
The square button, I think, is the stop, so you wouldn't have to redo everything every single time.
where here? No.
Right? Below the pause.
Oh yeah. Okay.
Yeah, that square button's probably a stop.
Oh yeah, but I don't know if I can change. No, I cannot change it.
No, the one.
Oh,
That.
here.
See? Now you can change it.
Oh,
So you
okay.
can keep your settings between.
Are you right? Okay, so now you can mix an electric field and a magnetic field, and you can get interesting motion. Isn't that cool? Okay. Okay, so let's practice now. So sometimes it's not easy to see what's going to happen. So the trick is, if for example, if you find a force to the right, it makes turn right. If you find a force to the left, that means turn left. So in that case, they already give you the solution, but I show you with my hand. So take your right hand. Take your right hand. So I show you here. Take your right hand for the positive charge here. Right hand. It's moving this way. Do you agree? Magnetic field is towards you. Do you agree? Yes. And the force is down. So that means turn down. So the motion will be this way. If it's negative, it's going to be the opposite. Okay? So you have to look at the force to know which way it's going to turn. It's not that easy. So the force is going this way, positive here. Magnetic field is towards you. The force is down. So it's going to make a turn this way. Negative will go turn the other way. Okay? You can practice with this one. See, the velocity is this way. The field is into the screen. Turn that way. Same thing here, velocity this way, magnetic field goes into the ball, turn that way. Okay? So not that easy. Okay, let's go back to okay. Understand this. So what's the idea now is we can use that idea to build a mass spectrometer. So I don't know, can you see this image here? Okay, so let's say you have a bunch of isotopes. So same velocity, but different masses, and same charge. So I don't know, like isotope of, I don't know what isotopes you have, but a bunch of isotopes with different mass. So it's coming inside this region here where you have a magnetic field. So can you see the velocity is this way, magnetic field is towards you, it's going to make a turn. When you increase the mass, what's going to happen to it? Do you make like you apply when you have a turn, when something is making a turn on the highway? Which one will make the sharp turn? The Ferrari or the big truck? Ferrari, right? So smaller the mass, sharper is the turn. So the radius will be inversely proportional to the mass. Does it make sense? Okay, inversely proportional to the mass. Now, if what's going to happen if you have more velocity? The radius is, what did I say? No, opposite, right? If you have a large truck, what did we say? Ferrari sharp, right? A truck larger. So the radius is proportional to the mass. Larger mass, larger radius. Do you agree? Okay. What about the velocity? The Ferrari is going 100 miles per hour versus 20 miles per hour. Which one will make the larger turn? If you go really fast, yeah, 100 miles per hour has more momentum. It will be harder for the force to make it turn. Okay, so the radius is larger for larger speeds. Make sense? Okay. What about the magnetic field? If you increase the magnetic field, you increase the motivation. So what can happen to the turn? it's going to get sharper. It's like motivation. Okay, go, go, go. I'm going to increase the magnetic field. Turn, 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 turn. You're increasing the motivation. And same thing with the charge. If you increase the charge, you increase the motivation. So it's more willing to make that turn. Okay? We can do the math, but at the end, you can get that equation just with the guts. With a truck and a Ferrari. The radius, okay, will be the momentum, so mass times the speed, larger momentum, okay, larger the turn, okay, it will be harder to stop it, and it's inversely proportional to the charge, inversely proportional to the magnetic field. So why are we using this? Because if you keep everything the same, so the velocity is the same, the charge is the same, and you magnetic field is the same, you can sort out isotopes according to their mass. So this is called the mass spectrometer. So all the isotopes, okay, have the same charge, they have the same velocity, they go inside the magnetic field, and the radius only depends on the mass. So you can move a detector up and down, and you can collect your isotopes, you can find the relative abundance of the isotopes, or you can find the mass of an isotopes, or you can sort out isotopes according to their mass. Isn't that cool? So when they did the atomic bomb for the Manhattan Project, they had to enrich uranium. Enrich uranium because uranium has two isotopes, more than two, but it has 235, 238. To make the bomb, you need 235. And you cannot use a chemical reaction to separate 238 from 235 because chemically they behave the same. Okay? But you use a magnetic field because uranium-235 will make a sharper turn, uranium-238 will make a larger turn, and you can collect uranium-235 again and again and again and again until you reach the critical mass that you need to make the atomic bomb. That was all the thing about the Manhattan Project. Now they don't do that anymore. That was back then. They use different technology, like in Iran, for example, they use a centrifuge, right? The same idea of centrifuge, it's all about the centripetal force. Okay, centripetal force depends on the mass, right? Okay. So I will let you do this one. We did this one. Well, this one is easy. Okay, just in your mind. Do it in your mind. I mean, just lay out your equations in your mind. When there is no angle involved, is QVB and then times the sign between the velocity and B. So is there a force here? No force, because you need the velocity to have a component perpendicular to B. So there is no force. Sine of 0 is 0. Are you with me? Magnetic force is QVB sine B. Is there a force here? Yes, so is it toward you or away from you? Towards you, right? V, B towards you. You can do the three fingers this way, towards you. Okay, this one is away from you. Okay, and you can do the math. QVB, blah blah blah. You see, you just multiply. Q. This is the charge of an electron. That will be the speed times the magnetic field. Okay. It says do it quickly. Okay, so let's do it quickly. Okay, let's choose just number one, just to plug it in. Number one. So I'm running out of paper. Uh, let's see, QF equals Q. One way you can write it this way. Okay, that's one way to do it. Okay, so F equals Q, V, and you put a perpendicular here. That means magnetic field here, the component of the magnetic field perpendicular to V, because it's a cross product. Or you can say F equals Q, B, a little perpendicular here. That means the component of the velocity perpendicular to the magnetic field. Because if the velocity has two components, let's say the velocity has a parallel component and perpendicular component to B, only this one will be involved in the magnetic force. This one, the parallel component, will make the particle move forward, right? But it will not deflect it. So it will have some momentum, but it will not be deflected. Only this one will make it, will make the deflection. Okay? Or you can say F equals Q, B, V, and then the sign. It's the same thing. So anyway, so this one is easy, right? So you go the charge, so 30 times 10 to the negative 9, and then the velocity, and then the magnetic field, and they are parallel to each other, so that will be numerical expression. Any question? So let's take an example here. Is there a force here? No, because it's either parallel or anti-parallel. So there is no component of the velocity perpendicular to B. There is no magnetic force. In that case, yes, you're gonna have a force. Again, velocity, magnetic field, force is up. That will be the maximum force. And it's going to make a turn, right? It wants to keep going along a straight line at a constant speed. So it's going to circle around in this direction. You see, it's going around the magnetic field lines. Magnetic field line going this way, it's going to go around. Do you see that it's going around? Do you see my mouse? It's going this way. In this plane here. And here there's a force, but you have to take the sine of that angle here. Okay, so it will QVB times the sine of this angle there. Agree? Or you see, you can say, okay, I'm taking, this is V, and you only want the component of V perpendicular to B. Any question? Okay, so that will be the answer. You have the force, and then force divided by the mass, that will be the acceleration, but that will be the centripetal acceleration. It's not an acceleration that you are going to change the speed, you are only changing the direction. This one, it's for the electron. So you see the mass of the proton, the mass of an electron, that's why the acceleration is not the same. Okay, so this one, right, okay, this one I'm gonna have an issue because I need my tablet. So I don't have my tablet, which is because I forgot. Not that I forgot, because I removed it because it was too heavy and I forgot to put it back. So I'm going to show you a simulation. Because I really need my tablet for this one. Okay, so here let's practice conceptual question. Let's take the particle positive. Okay, which way is gonna turn? So it's like a mass spectrometer, and you can move the detector. Detector can be moved here. I cannot move it, but yes, I can move it. Okay, so which way it's gonna go? To the right or to the left? We say don't. To the right or to the left? Help each other. Do it with your right hand. So cross means magnetic field goes into the screen, yes? Okay. So velocity is up. Magnetic field goes into the screen. Left, very good. Left. Do you agree? Okay, let's see. Yeah. Left. Now, if you have a negative charge, it will go to the right. Yeah. See? Now, if I increase the velocity, so it's going to have more momentum, more momentum, harder to steer. When something has more momentum, it's very hard to steer. So more momentum, let's see what's going to happen. Look at this. I got it. Okay, so the radius will be larger with more momentum. Agree? So this is more momentum. Now, if so, let's say where are we? So let's go back. Let's go back to here. Now, if I increase the magnetic field, I'm going to increase the motivation. Okay, so steering will get easier. Ping. You see that? So larger magnetic field, smaller radius because you increase the motivation to steer. Larger charge also. Larger charge means bigger motivation, so easier to steer. Okay, this one is super interesting because it's some calculus, but I leave it because I don't have my tablet. Okay, so let's do more conceptual stuff. So what do you think alpha is? So they did that in the 1930s when they started to detect all those particles, and it's particle physics. So they developed the cloud chamber and the bubble chamber. So the bubble chamber and the cloud chamber. And the idea is that you have like a chamber, right, with some gas inside, like let's say alcohol vapor, for example, almost to saturation. And then when you have a particle coming from space, every second you have tons of particle cosmic rays going through your brain right now, going through your brain and going through your brain, right, non-stop. So when it goes through that chamber, those particles coming from space, or you can also produce those particles yourself. It's going to leave a trace in the chamber. Okay, so because it's going to kick those gas molecules that will turn into a liquid, and then you see you apply your magnetic field. The magnetic field will steer them, deflect them, and as they go around, they're going to lose some kinetic energy. So that's why the spiral here gets tighter and tighter. That's how they discover the positron, the anti-electron. Okay, so anyway, a magnetic field will deflect a particle. So alpha particle, what do you think this is? Positive or negative? Take your right hand if you don't know alpha particle. Positive. Okay, you take north to south, and then no, just kidding. Velocity, north to south, force it up, So it's positive. So alpha particles, they didn't know what they were. So before, when people were very educated, they will take Greek and Latin. So instead of saying X, Y, Z, they will say alpha, beta, gamma. Okay. So alpha had no idea what it was, so it's like X, unknown. It's nuclei of helium. Okay, it's radiation. And gamma, what do you think about gamma? Is that positive or negative? Gamma, is it deflected? No, neutral. So what is gamma? Gamma rays. It's gamma ray. No, photons. It's light. It's invisible light. Okay, part of the electromagnetic spectrum. You have radio waves and microwave, infrared, visible light, UV, X-ray, gamma ray, PET scan, gamma ray, radioactive stuff, gamma ray, radio, gamma ray, very damaging, very damaging, very small. And what about beta? Is it positive or negative? Negative, okay? Beta are electrons. Beta plus are positrons. So these are radiations. From you get them from radioactive decay, for example. Okay? Beta, it's bad. Alpha, it's not that bad if you don't get it inside. You know, it will be stopped by your dead skin. Gamma, very bad. So I'm not going to ask you to build that, but you could. If you like hands-on stuff, you could. You could build your cosmic ray detectors because you have particles coming from space all the time. So you have an aquarium here, you have a heated pad, and alcohol is almost to saturation. So each time you have a particle coming from space, it will leave like a trace. Okay, ready for the music? It's a super cool music. So heating pad, here, alcohol. You see here, there, here, coming from space. It's your own cloud shampoo. Oh, look at this one. This one coming from space, coming right now for your brain, every second for you. Oh, did you see this one? It's particles coming from space, maybe from the wall. Could come from the wall, you know, from the floor. It's good, right? It's gonna wake you up. All day long, you're gonna have this music, you're gonna hate me. This one is good, this one, this one, this one, this one, here, there, I think here. So we're gonna have a physics ref party, you know? Okay. Yeah, there's a pop quiz. You can do that. It's possible. It doesn't even cost too much money, right? It's cool to do. Extra credit if you do.